Well, welcome back. This week we're gonna discuss MapReduce. So first of all, uh, let's try. Let me try to refresh you about some concepts that we have been discussed before. So first of all, is the data structure in MapReduce. So key value pairs are the basic data structure in MapReduce. The key value pairs are what you transfer between one RDD to another, if you still remember, right? So here the key and values can be integers or float or strings or row bytes or even other arbitrary data structures. So the design of MapReduce algorithms is all about key value pairs to some extent. For example, we need to impose the key value structure on arbitrary datasets. We need to decide what is key, what is value. So basically, key is the identity of elements, where the value usually will be the number that to be combined or aggregate together. But the value could also be, for example, strings, if you want to add strings together or concatenate them together. For example, in word count, if you still remember, the key is word. Right? And the value is the frequency of the word. So if we consider a character count, for example, then the key would be a character and the value would be frequency. Right. But if we consider a frequency count, for example, say the goal is to count. Say if we know that the frequency of word 1 is 10, the frequency of word 2 is 9, and the frequency of word 3 is 10. So the goal of our program is to output this kind of information, saying there are two words has frequency of 10 and one word have frequency of 9. So the key value pairs as your result would be the frequency and the count, while the key values at a certain stage of this MapReduce procedure would be word and frequency. So the key value pairs could change, of course, and their types and the meanings behind them totally depends on your purpose and your design. All right. So here's another example. Say for a collection of web pages, input keys could be URLs, and the values could be the HTML content. In some algorithms, the input keys are not used. For example, in word count, the input key would be a document ID where the value is the content of the document. So if you still remember, the first thing we do is to use a flat map to to extract the terms of in the documents. So we would have a list of word and one pairs. if you still remember what we have discussed before, right? So in this case, the input keys are not used. It is possible, but in other cases, or in most cases, the keys uniquely identify a record, especially in those applications regarding to a database or a table. The keys can be combined in complex ways to design various algorithms. So basically, it depends on your objective and your design. For example, we have keys like this, the, and bad, better, if you think. So the purpose is to combine to count the occurrence based on their first character. So what say their frequency is 1 at first for all of them. So what we want to have is as the final goal would be something like this, right? So in this case, keys are combined together. In this case, based on their first character. So we say they can be combined in complex ways to design various algorithms. All right. And recall of the concept of map and reduce. So map reads data and produces key value pairs as intermediate outputs. So the data here is in Spark is RDD. In Hadoop is a file that is split into several splits or blocks. Yeah, we will discuss this later. For reduce, it receives key value pairs from multiple map jobs and aggregates the intermediate data tuples to the final output. So basically, when we design a MapReduce program, we need to fit everything into this map and reduce framework. Right. So that is the concept of map and reduce. Now let's look at MapReduce in Hadoop first. So in today's class, we probably still will still through some time on Hadoop. So for MapReduce in Hadoop, the data stores in HDFS, right? Organized as blocks. We have discussed a lot about this, right? So in Hadoop, the MapReduce divides input into fixed size pieces, or say the input splits. And for each split, there will be one map task creates for it. And the map task runs the user-defined map function for each record in the split. So the map task is run for each record in that split. In the split. Right. The size of the split is normally the size of a HDFS block. The reason of this setting is because of this data locality optimization. So when we run the map task on a node, we hope that the node is where the input data resides in HDFS. So this is the reason why the split size is the same as the block size, because the largest size of the input that can be guaranteed to be stored on a single node is the block size. So if the block size larger than if the block size larger than the split size, if the split size larger than the block size, then it cannot guarantee that the data would be on the same node. So you're gonna, for the node here, it contains a part of the data is come from itself, but also another part of the data would come from a remote node. Then there would be extra cost to read these data. Right. On the other hand, if the split size smaller than the block size, then what will happen? So basically, because we will, in this case, apparently we would have more nodes involved, which means more network communications between these work nodes. Well, compared to this, the benefit from more work nodes, which is we would do the computation faster because the data split is smaller. But compared to the network communication and the data transportation between work nodes, the benefit is not that important. So this is for MapReduce in Hadoop, the data locality optimization. Right. So the map tasks will write their outputs to local disk, not to HDFS. So this local disk is the disk on the work nodes, or hopefully the data nodes that contains the block. Right. So remember, not to HDFS means this data, the output here, will not be recorded by the name node, right? And as you would see that once the job is complete, right, this output can be thrown away, because they are just intermediate output. They're not the final results. Right. And if we write it into HDFS, then we need to do replication. In this case, I mean, it would be overkill again, because this output is intermediate and will be totally useless after the job is complete. In the case that the node of the map task fails, Hadoop will automatically rerun the map task on another node, especially because we have replications. So the Hadoop will, with high probability, will find another data node that contains the same block and to rerun the map task. So this is the good thing about, if you still remember, the good thing about replication, where you can have this data locality thing. However, if you use erasure coding, then the work node will read the data from 6 or 5 if itself contains part of the block. So we'll read the data from multiple data nodes to recreate the block or the part of data, which means there is no data locality for this if the file is using erasure coding for a fault tolerant guarantee, right? And also the reduced tasks don't have the advantage of data locality, because the input to a single reduced task is normally the output from all mappers. Note here it says normally, so this is because it depends on whether shuffle is happened or not, which we will discuss later about shuffle. But in most cases, if you still remember, say this is the map stage. But for reduce, I mean, the input of a single reducer would come from different map tasks. So in this case, it doesn't matter the reducer have part of the data or not, because for one, the data is already being mapped, so it's not the original data. For two, data comes from different map nodes. So the reduced tasks cannot benefit from data locality. The output of reduce is stored in HDFS for reliability, because if the output of the reduce is the final output, then definitely it would be stored in HDFS. If the task is like iteratively, like we train a model, a machine learning model, we need to, for each iteration, we have a reduce task. And the data output by the reduce task for that iteration is stored in HDFS, because once the let's say on the third iteration, if a node failed, right? If we recreate the data from the very beginning, then we need to repeat the whole procedure. But if we have the output of the reduce for the second iteration stored in HDFS, then we just load that, and then in the meanwhile, we don't need to do the first two iterations again, right? So this is the output for the reduce. The number of reduced tasks is not governed by the size of the input, but is specified independently. So the number of reduced tasks could be more than or less than the number of map tasks, right? It would be specified by the user. Okay, so for more detailed MapReduce data flow, when there are multiple reducers, the map tasks partition their output. Say for each reduced task, there would be one partition, and they have to guarantee that the records for every key are all stored in a single partition. Right? Means let's see the example here. So there are two reducers. That's why for each map, the result is is partitioned into two partitions, right? And we need to guarantee saying that for each map task, the output, there will not be a key. I mean, one key could have multiple values, or could correspond to multiple key value pairs. Say if we have a key 1, value 1, key 1, value 2, and key 2, value 3. This is the output for one map task, and if we do the partition, we can only partition it in like this. so for key one, the key value has to be resides in one partition. If we partition them into like this, then it is incorrect, because they will go to different reducers. So for the same key value, the key one, they will go to different reducers, but the reducer itself, there will be no data exchange between reducers. So if we want to, let's say we want to sum up the values for the same key, right? So what we need is key 1, v1 plus v2. We cannot do that, because for reducer 1, it only has key 1, v1. For reducer 2, it has key 1, v2. So they cannot add v1 and v2 together. So this is not an option. Right, that's the reason. And for the similar reason, we would like the partition criteria be the same for different mappers or map tasks, such that all the key 1, let's say so all the key 1 would goes to reducer 1, let's say, and all the key 2 would goes to reducer 2. Otherwise, if the reducer only have data of key 1 from mapper 1, and the reducer 2 has data of key 1 from mapper 2, let's say, again, because they cannot interact with each other, so there's impossible for us to grab such kind of information. And the partition can be controlled by a user-defined partitioning function. Right. And this partition from mappers to reducers, here, is also called a shuffle. So shuffle is the process of data redistribution, and is a very important component of MapReduce. Although in Hadoop, shuffle is handled by the MapReduce of Hadoop, and also in Spark, the shuffle is handled by Spark. But it is still important for us to know how it works if we want to avoid, say, inefficient design of MapReduce. Right. So shuffling is to make sure each reducer obtains all values associated with the same key, which we have been talking about before, just before, right? So it is needed for all of the operations which require a grouping. So by grouping means you kind of group the records or the elements based on the key value, right? For example, in word count, we're grouping based on the word to then do the counting, right? Or when we compute the average score for each department, then we need to group the records or the scores based on the department. So in this case, department is the key, right? Then we do the compute the average. So basically, Spark and Hadoop MapReduce actually have different approaches implemented for handling the shuffles. So shuffle in Hadoop, as I said, it is handled by the framework. So the shuffle in Hadoop happens between each map and reduce phase. So the processing is to transfer data from the mappers to the reducers. So in Hadoop, it uses a shuffle and sort mechanism, where the results of each mapper are sorted by the key and waited to be sent to the reducer. So this shuffle and sort mechanism starts as soon as each mapper finishes. So basically, once the mappers are done with the calculations, the results of each mapper are sorted by the key in so-called buffers. And once the buffers are filled up, the data spills on the machine's local disks. If you still remember, the intermediate result of map will be stored on the local disks, right? And it will be removed as soon as the job finishes. So this shuffling happens as soon as each mapper finishes its job, because in this way it will tries to not overflow the network. So we don't need to wait for all the mappers to finish and then send the data. So basically, one mapper finishes and it can then send the data, right? And it depends on the settings. The reducers may also start running before all mappers have finished their jobs. And sometimes we use a combiner to reduce the amount of data shuffled. So the idea of combiner is to combine key value pairs with the same key with the same key in each pair, in each partition. Sorry. And this is not handled by the framework. So basically, you need to do it by yourself. Because let's say whether use or not, whether use the combiners or not, or how to use the combiner is totally depends on the problem itself and your design. For example, let me say word count, right? You have W1 1, W1 1, W1 1, W2 1. Let's say you have this on your mapper, and by combiner we mean we combine the key value pairs with the same key. So we combine this 3 W1 together. Since we're doing the word count, then we write a 3 here. And because there is only one W2, so W2 1 is remains here. So this is where the combiner does. However, this is for us to do the word, let's say word count. But what if we do, let's say, compute the average, right? So we have W1 2, W1 3, on the other hand, W2 4, and W2 5, W2 1. Right. So if we want to do the calculate the average, we cannot simply add the values together, because if we do so, we would have W1 5 and W2 is 10. Right. Then the reducer would have 5 and 10, but it does not know the total number of W1 and W2 here, so it cannot do the math to compute the average number. So in order to let the reducer be able to do its job, we would also need to record the number of W1 and W2. So if we do the combiner like this, then the information is useful for the reducer to calculate the average number. Now let's see the example of MapReduce in Hadoop. While we have seen this before, I do hope that we could have a better understanding of this whole procedure for now. So the input is split into splits. In HDF in Hadoop, it's the block. The size is the block of the HDFS. Right. So these are so this is the file, and this is the block, or say the splits, right? So they reside on different data nodes. Because of the locality optimization, so hopefully data node 1 do have this part of this block, and data node 2 have this block, and so on and so forth. Remember, our goal is to count the frequency of the word, and because of the data is too large, each partition or each node do not know what the other nodes like. So for the mapping, it's just map the sentence into this key value pairs, where the value is always 1 for each key. The key is the word, right? For shuffling, it actually groups the same key together to a same partition. So for this partition, for this partition only contains the key of bear and the car here, deer, and river, so on and so forth. And for reducing, it will add up the numbers here to get the total number of this word, and finally it will be aggregated together. So if we want to do a combine here, for example, we have here we have 2 cars. Yeah, we have 2 cars in this block, right? So for combiner, it will combine this key value pairs with the first one. So here should be 2, and this will not be exist anymore, and it will affect the shuffling procedure as well. So here you would have car 2 for one record, and another car 1 is from here, right? So and then you do the reducing. Now the reducer and the mappers, can they are on the same machine or not? Actually, they can, right? Well, they can, or they're not, is also possible. As we have discussed before, the data locality, because reducers cannot benefit from it, so basically it doesn't matter whether there's on the same machine or not. But definitely it can, and if the reducer and the mapper is on the same machine, then hopefully the data transferred from mapper and reducer would be faster, because there would be no data transfer through a network. So that's pretty much for MapReduce in Hadoop. And now let's look at MapReduce in Spark. So we start from Shuffle again. So Shuffle in Spark, which is handled by Spark again, there are quite a lot of differences between Shuffle in Spark and Shuffle in Hadoop. So for example, the Shuffle in Spark is triggered by some operations. not as in Hadoop, shuffle is triggered by the reducer, right? When you are going to transfer the data from mapper to reducer, you need to do the shuffle. But here in Spark, shuffle is triggered by some operations. So these operations include a distinct, join, or repartition, or all the by operations, like repartition by, or those are by key operations, like reduce by key or group by key, which we will discuss in detail later. So if you still remember the conception of the concept of stage, so this shuffle actually happens between stages. So just in case you're not remember, so there are two kinds of transformations, right? Wide and narrow. So narrow transformations is from is something like a one-to-one transformation. So it's from one partition to another. But for wide transformations, it transfers data from so the partition of the result of the wide transformation, the data in that partition comes from different partitions, right? So as you can see here, so this is a classic shuffle operation, and we cut the stages in Spark based on wide transformations. Right? So once there are a new stage, means we have a shuffle. So there are two ways in Spark to perform shuffle. One is based on hash, and another is based on sort. Actually, there is a third method called tungsten shuffle sort, which we will not introduce in today's lecture. If you are interested, here is the link, or you can Google for. So hash shuffle. In hash shuffle, data are hash partitioned on the map side. So the good thing of hash shuffle is that hashing is more faster than sorting. So if you still remember, the purpose of shuffling is to group records based on the keys. So one way, so the traditional way is to use sorting. Such that, for example, we have keys of 21323. After sorting, it would be 12233. Then the key is naturally organized. But if you I think you must have learned about this. So basically, the sort algorithm, the time cost was usually big O of n log n. Right. On the other hand, if we use hashing, we may not have this exact order, but we would have something like so we actually have the hash value of each of the key here, and we do have the property that if the two keys are the same, the hash value would be the same, and if the keys are not the same, then with high probability the hash value will not be the same. So in this case, we can also distinguish them, but the time cost of hashing is big O of n, because each hash operation, the time complexity would be big O of 1. All right. So these are the the good thing about hash shuffle. But hash shuffle will create files to store the partitioned data portion. So let's say let's define the mapper and the reducer. Although there is no mapper and reducer in Spark, but let's say we define the mapper is the one before shuffle, and reducer is the one after shuffle. Right. So it is the last operation of the previous stage and the first operation of the next stage. Right. So when do hash shuffle, it calculates the amount of reducers as the amount of partitions on the reduced side. And for each mapper, it creates a separate file for each of the reducers. And looping through the records is need to output calculates the target partition for each of them and outputs the record to the corresponding file. So basically for one mapper, let's say there is 3 reducer, then it will create 3 files and write the data into different files, also partitions, based on their key, right? So for each mapper, it will create a number of reducers files, and we do have this number of mappers. So we have the multiplication of the number of mappers and the number of reducers as the total number of created files. So the problem is that the number of created files is too large, right? And the output buffer size is limited. And the speed of creating and dropping these files becomes the bottleneck of the hash shuffle. Right. So in order to overcome this, we use consolidated files to reduce this total number of files. So instead of creating new file for each of the reducers, it creates a pool of output files. Then when map task starts outputting the data, it requests a group of R files from this pool. So basically, it's like we have a pool of R files here. And each time a mapper will take these files, write in these files, and send them back. And the next mapper will do the same thing for each of the files here. Now assume that the E is the number of executor. The C is the number of core, and the T is the number of CPU. So basically, for each executor, it can only execute C over T tasks in parallel. So it would create only C over T groups of output files, and each group is of R files. So after the first C over T parallel map tasks has finished, each next map task would reuse an existing group from this pool. So the total number is reduced from M times R to E times C over T times R. So now the advantage of hash shuffle is it is faster than sorting, but and there is no memory overhead because of there's no memory overhead of sorting, right? But the disadvantage is the large amount of output files, especially when the number of partitions is big or the number of reducers is large. So interestingly, I mean, the hash shuffle is created or proposed to overcome the shortage of sort shuffle, but when but very soon, I mean, the designers of Spark actually realized that hash shuffle has its own problem. So they goes back and use sort shuffle again. Right. So for sort shuffle, for each mapper, two files are created. One is the ordered data, and another is the index of beginning and ending for each chunk. Here, for example, if we have the data ordered by key, let's say W1, W2. Let's say the data is like this, right? So there are two files. The first file is just the ordered data, like in red, and the second one is the index of beginning and ending for each chunk. So a chunk is it's all the data with the same key combined together and forms a chunk. So it will record the beginning and the ending of each chunk. So this are formed as a index. All right, and these files would be merged on the fly while being read by reducers. And also, I mean, if the map side combination is required, then the data is not only sorted but also pre-aggregated by partitions. So it will reduce the size. It will further reduce the size. All right. So the default way is to use a sort shuffle, but when the number of partitions is small, it actually falls back to hash shuffle. So it is important to find a sweet point, because when the number of partitions is large, hash shuffle is inefficient. But when the partitions is small, hash shuffle is better. So we need to find the sweet point to overcome the trade-off here. And the advantage of sort shuffle is that the smaller amount of files are created, right? But the disadvantage again is the sorting is slower. So let's have a break, and in the second half of today's lecture, we will be discussing the functions of MapReduce in Spark, and how do we design efficient MapReduce process in Spark. Okay.